The universe is a place of unfathomable beauty and wonder, yet it is also home to the most terrifying and hazardous phenomena the human mind can conceive. Hidden within the vast reaches of space are forces that challenge our very understanding of reality, regions where the laws of physics are stretched to their breaking point. From black holes that hold everything within their grasp to cataclysmic supernova explosions and mysterious bursts of radiation capable of sterilizing entire worlds, these cosmic titans represent the pinnacle of destructive energy. Yet, within this chaos lies a strange balance. These lethal forces are not merely harbingers of doom, but the very engines of creation for stars, planets, and life itself. What happens when two supermassive black holes collide? How can a neutron star, no larger than a city, pack the mass of the Sun and lash the cosmos with deadly radiation? If a hidden variable star directed its jet toward Earth, could it release a torrent of high energy particles strong enough to wipe out life across a sector of space? Today's journey takes us through the most dangerous reaches of the cosmos to explore these mysteries, from the explosive birth of new elements in supernovae to the mind-bending concept of white holes, the time-reversed twins of black holes. It is a long story, so let us begin the exploration as we drift into the world of dreams. But before we start, remember to like and share. Stellar mass black holes are among the most elusive and dangerous objects in the universe. While we often focus on the supermassive black holes at the centers of galaxies, stellar mass black holes are far more numerous and may be much closer to us than we realize. Born from the collapse of massive stars, many of these predators reside in binary systems, orbiting a companion star and silently waiting for their moment to strike. In these pairings, one star often evolves faster, reaching the end of its life and collapsing into a black hole to become an invisible predator. The surviving companion continues to shine, unaware that its partner has transformed into something far more sinister. This is the hidden nature of stellar mass black holes. Unless they are actively feeding on a companion's matter, they emit no light and remain cloaked in darkness. Imagine a scenario where a black hole begins to slowly siphon gas from its neighbor, forming a swirling accretion disk. This process generates intense radiation, often appearing as X-rays, detectable by our telescopes. The sight of a star's outer layers being peeled away by a hungry black hole is as chilling as it is fascinating. Over millions of years, the black hole may entirely consume its partner, turning a once harmonious binary system into a graveyard. Their terror lies in the stealth. Many lie dormant until they feed, suggesting they could be much closer to Earth than previously estimated. Thousands of these invisible hunters likely roam the Milky Way. Beyond consumption, they can launch powerful relativistic jet streams of high-energy particles that travel vast distances. While the chance of such a jet hitting Earth is low, the radiation from a nearby event could devastate our satellites and atmosphere. We might only detect them when the surge of X-rays begins, leaving us little time to react. In the cosmic backyard of our galaxy, these cosmic landmines wait for the right conditions to reveal their presence. Moving to the heart of our galaxy, we find the Fermi bubbles, colossal structures of high-energy radiation spanning tens of thousands of light-years above and below the galactic plane. Discovered by NASA's Fermi Gamma Ray Space Telescope, these bubbles provide a window into the Milky Way's turbulent past. At the center sits Sagittarius A*, a supermassive black hole 4 million times the mass of the Sun. Though currently quiet, the Fermi bubbles suggest that our central black hole once underwent a period of extreme activity, blasting high-energy particles into space. Whether caused by a massive feeding event or a frantic burst of star formation, these bubbles prove that the galactic center was once a place of extreme violence. If Sagittarius A* were to wake up again, the resulting radiation could sweep through the galaxy. While our distance of 25,000 light-years provides a buffer, the bubbles remind us that we live in a bottleneck between periods of galactic upheaval. Among the most unstable stars in existence are Wolf-Rayet stars. These massive, volatile objects do not fade away, they exit the stage in the most violent manner possible. Burning with extreme intensity, they shed their outer layers via stellar winds moving at thousands of kilometers per second. A Wolf-Rayet star is essentially a ticking time bomb that may trigger a gamma-ray burst, the most lethal phenomenon in the universe. In certain supernovae, concentrated beams of gamma radiation are ejected from the poles, releasing more energy in seconds than the Sun will in its entire lifetime. If a star like WR104, located about 8,000 light-years away, were to explode with its axis pointed at us, the radiation could strip away our ozone layer and trigger a mass extinction. Though the risks are low, these stars represent a risk we cannot fully control. Yet, their deaths are also transformative, forging the heavy elements necessary for planets and life. Finally, we look toward the Great Attractor, a mysterious gravitational anomaly pulling our entire galaxy and thousands of others toward it. Located in the zone of avoidance, an area obscured by the dust and stars of our own galactic disk, its true nature remains a mystery. We observe its influence through the motion of galaxies. The Milky Way is currently racing toward it at roughly 600 kilometers per second. Whether it is a massive supercluster or something entirely beyond our current understanding of cosmic structure, the Great Attractor acts as an invisible hand guiding the evolution of the local universe. We are part of a cosmic flow, drifting toward a future shrouded in mist, as galaxies continue to converge and reshape the web of space-time. These forces remind us that the universe's greatest dangers are often the very same forces that define its grand design. In the unfathomable future, when the last stars have flickered out and the heavens have succumbed to darkness, what remains? Scientists believe one of the final legacies of stellar life will be black dwarfs. These entities originate from white dwarfs, the hot, dense cores left behind after low-mass stars exhaust their fuel. Over unimaginably long time scales, these white dwarfs will gradually cool and dim. When they eventually reach a state where they no longer emit detectable heat or light, they become black dwarfs, frozen spheres that blend almost perfectly into the cosmic background. We have never observed a black dwarf because the universe is simply not old enough for any white dwarf to have cooled to this point. Yet, in the distant future, the cosmos will be littered with these silent relics. Existing at temperatures near absolute zero and no longer participating in nuclear fusion, they will drift through the void in total isolation. These objects represent more than just the end of a star. they are a chapter in the ultimate fate of the universe. As stars fail to regenerate and useful energy is exhausted, the universe will enter a state of heat death, a thermodynamic standstill where light and warmth are relics of the past. In this graveyard of galaxies, black dwarfs will stand as scattered, silent tombstones. Their ultimate fate is still debated, perhaps, through incredibly slow quantum tunneling. Their internal particles will eventually decay and vanish, or they may persist indefinitely as the final protagonists of a cold, dark reality. Among the more exotic theoretical possibilities is the Thornzeitkow object, or TZO. This is a bizarre hybrid star formed when a neutron star is swallowed by a red supergiant and sinks into its core. From the outside, it looks like a typical red supergiant, but its heart is a superdense neutron star. This overlapping of two vastly different physical environments creates a star that functions unlike anything else in the cosmos, where extreme gravity and intense magnetic fields can trigger unpredictable eruptions of matter and radiation. While TZOs are exceptionally rare and current candidates remain controversial, they represent a high-stakes local risk. Their instability could eventually trigger a supernova-like explosion, drenching nearby space in high-energy particles. On a much larger scale, when galaxies merge, the supermassive black holes at their centers are drawn together by gravity. This is one of the most majestic and violent events in the universe. In a slow-motion dance lasting millions to billions of years, space-time itself is violently warped as the black holes spiral inward. Near the event horizons, time nearly stands still, and surrounding stars are reshaped by tidal forces. The final collision releases a colossal burst of energy in the form of gravitational waves, ripples in the fabric of space-time that travel at the speed of light. We first detected these ripples in 2015, proving that black hole mergers are real. For the Milky Way, a similar fate awaits in several billion years when we collide with the Andromeda Galaxy. Our central black holes will eventually meet, setting the night sky ablaze with the glow of friction-heated gas and the distortion of stellar orbits. Even the seemingly stable white dwarfs hold a hidden danger. In binary systems, a white dwarf can stealthily siphon matter from its companion star. As its mass approaches the Chandrasekhar limit, the internal pressure triggers a runaway thermonuclear reaction, and the star is instantly detonated as a Type 1a supernova. The terror of these events lies in their lack of warning. A white dwarf looks stable until the very moment it explodes, becoming a silent killer. A nearby explosion could strip away a planet's ozone layer through a flood of X-rays and gamma radiation. Yet, these events are also vital standard candles that help astronomers measure the expansion of the universe and understand the influence of dark energy. In the deep, freezing reaches beyond our planets lies the Oort cloud, a gargantuan reservoir of icy bodies extending nearly a light-year from the Sun. While we cannot see it directly, long-period comets tell us it is there. The danger of the Oort cloud lies in its fragility. The gravitational tug of a passing star or galactic tides can kick these icy giants into the inner solar system. These comets can be massive and travel at incredible speeds, and unlike near-Earth asteroids, they offer very little warning time, sometimes only months or weeks before a potential impact. Looking into the heart of density itself, we find the theoretical concept of Planck stars. This idea suggests that at extreme densities, quantum gravity effects prevent the formation of a singularity, stopping the collapse of a star at a finite, ultra-dense state. If they exist, Planck stars would be nearly impossible to detect via radiation, yet they would roam the galaxy as invisible gravitational disruptors. Similarly, we look at blazars, active galactic nuclei, where a supermassive black hole's relativistic jet is pointed directly at Earth. These jets are not just light, they are streams of charged particles moving at near light speed. While the known blazars are currently far away, the unpredictability of when a dormant black hole might wake up and fire such a jet makes them the universe's most intimidating spotlights. Finally, we consider the life cycle of neutron stars and the evidence of the unseen. When a massive star dies, it may leave behind a core so dense that a single teaspoon of its material would weigh 1 billion tons on Earth. These neutron stars can become pulsars, lashing the universe with precise beams of radiation, or even evolve into more exotic quark stars. To understand the scaffolding of all this, we look to the bullet cluster. This snapshot of two galaxy clusters colliding provides the best evidence for dark matter. While the visible hot gas slowed down during the collision, the majority of the mass, the dark matter, passed right through without stopping. It reminds us that most of the universe is made of things we cannot see, yet it is their gravity that ultimately scripts the fate of every star, every galaxy, and every living thing. Beyond the colossal collisions of galaxy clusters like the bullet cluster, where we see the distinct separation of visible gas and invisible dark matter, we find that the very fabric of reality is held together by forces that are as silent as they are powerful. At the heart of every atom lies the strong nuclear interaction. While the electromagnetic force should cause positively charged protons to fly apart, the strong force acts like an unbreakable tether, binding nucleons together with a strength 100 times greater than electromagnetism, albeit over a very short range. Deeper still, protons and neutrons are composed of quarks, held together by gluons. These gluons act like invisible springs. Because of a property called color confinement, no quark can ever exist in isolation. The harder you try to pull a quark away, the stronger the tension becomes until the energy of the pull snaps, creating a new quark antiquark pair from the vacuum rather than letting a single quark go free. This interaction does more than just shape the nucleus, it is the engine of the stars. In the solar furnace, the fusion of hydrogen into helium converts a tiny fraction of mass into the energy that warms our world. From the forging of elements in stellar interiors to the violent birth of heavy metals in neutron star mergers, the strong interaction dictates the rules of stability, radioactive decay, and the power of the atom. In the extreme heat of the early universe, matter existed as a quark-gluon plasma, and only as the cosmos cooled did the strong force freeze quarks into the protons and neutrons that make up our existence today. Using the Large Hadron Collider and the relativistic heavy ion collider, we briefly recreate these primordial conditions to study the limits of this fundamental glue. Nearly 93 million miles away, our Sun stands as a testament to these forces. Its core, though occupying only 20% of its radius, contains more than half its mass, with temperatures reaching 15 million degrees Celsius and pressures 250 billion times that of Earth's atmosphere. Here, hydrogen nuclei are crushed together to form helium, releasing mass as pure energy. Every second, the Sun converts 600 million tons of hydrogen, losing 4 million tons of mass to light and heat. This energy wanders through the radiative zone for hundreds of thousands of years before reaching the surface, yet once it escapes, it reaches Earth in just over 8 minutes. Traveling alongside this light are neutrinos, ghostly particles that barely interact with matter. Trillions pass through your body every second, serving as silent witnesses to the nuclear fusion occurring in the solar core. Currently in the middle of its 10 billion year lifespan, our Sun maintains a delicate balance between the inward pull of gravity and the outward push of radiation pressure. Eventually, it will expand into a red giant before leaving behind a cooling white dwarf, but for now, it remains a dynamic, storm-tossed sphere. Its magnetic fields twist and reconnect, triggering solar flares that release the energy of billions of hydrogen bombs. These flares, ranked from A to X class, can disrupt global communications and satellites. Even more powerful are coronal mass ejections, or CMEs, colossal clouds of plasma weighing billions of tons that can trigger geomagnetic storms, threatening power grids and GPS systems on Earth. While our atmosphere and magnetic field shield us, our technology remains vulnerable to these solar outbursts. If you were to venture toward a black hole, you would experience one of the most bizarre phenomena in physics: spaghettification. This is the result of extreme tidal forces, where the gravitational pull on your feet is significantly stronger than the pull on your head, stretching you into a thin strand of matter while compressing you laterally. In a small stellar mass black hole, these forces would tear you apart before you even reached the event horizon. In a supermassive black hole, however, you might cross the horizon intact, only to be pulverized as you approach the singularity. From the perspective of an outside observer, your time would appear to freeze at the horizon, your image reddening and fading into nothingness as you enter a region where every path leads inevitably to the center. The universe also harbors the ultimate energy source, antimatter. When a particle meets its antiparticle, such as an electron meeting a positron, they annihilate, converting 100% of their mass into pure energy. A single gram of antimatter reacting with a gram of matter would release energy equivalent to a 20 kiloton nuclear explosion. The mystery remains why our universe is composed almost entirely of matter. A slight asymmetry in the early universe allowed matter to survive by a margin of 1 in a billion. While we can create antimatter in labs, its storage is incredibly difficult and expensive, requiring magnetic levitation to prevent it from touching the walls of its container. Today, antimatter helps us test the fundamental symmetries of physics, and the detection of gamma-ray signatures in our galaxy may point to areas where matter and antimatter are still locked in a cosmic dance. To understand these complexities, we turn to supercomputers. Simulations like Illustris and the Millennium Simulation allow us to grow billions of virtual galaxies, tracing the interplay of dark matter, gas dynamics, and black hole feedback across 13 billion years. These digital universes are essential for interpreting the massive amounts of data from instruments like the Event Horizon Telescope, which stitched together the first image of a black hole. Deep underground at the LHC, we push the boundaries of high-energy physics, searching for answers to why gravity is so weak or why matter dominates the cosmos. We also observe clocks in the sky, such as type I X-ray bursts on neutron stars. These occur when a neutron star siphons hydrogen and helium from a companion star, creating a thin layer on its surface that eventually ignites in a runaway nuclear explosion. These bursts provide a unique window into the extreme physics of dense matter. Finally, we face a new challenge from the James Webb Space Telescope. Traditional models suggest that dark matter provides the gravitational scaffolding for galaxies. However, some of Webb's early observations of ancient galaxies show them to be surprisingly well organized and light, seemingly lacking the massive dark matter halos we expected. Some of these early galaxies appear so stable and smooth that they challenge our understanding of how structure formed in the infant universe. While it is too early to discard the dark matter model, these findings have revived interest in modified Newtonian dynamics, or MOND, which suggests that our laws of gravity might need adjustment at cosmic scales. Whether the answer lies in a new type of dark matter particle or a fundamental change in our understanding of gravity, we are standing on the threshold of a new era in cosmology. Each new image from the depths of space is an engine of discovery, forcing us to rethink the very rules of the universe we call home. Perhaps dark matter is not always perfectly aligned with ordinary matter. Perhaps in the early universe, it was more diffuse, or its properties shifted over time. If so, we would need to rewrite the entire timeline of galactic formation and evolution. Regardless, the dark matter fingerprints emerging from JWST data are forcing astronomers back to a fundamental realization: our models are merely maps, and sometimes, new data reveals that the map is not the territory. Astronomers once believed they had planetary systems figured out: small rocky planets near the star and gas giants on the outskirts, just like our solar system. That neat, orderly picture collapsed with the discovery of exoplanets. We found worlds that defy every rule, gas giants that orbit their stars in mere days, and massive rocky frozen blocks at the edges of their systems. Now, the James Webb Space Telescope has joined the hunt. It doesn't just count planets, it peers into their atmospheres, dissecting their composition and their interactions with their host stars. One of the greatest surprises has been the sheer abundance of hot Jupiter's gas giants similar to Jupiter but orbiting so close to their stars that a year lasts only days or even hours. Baked by intense stellar radiation, their surface temperatures soar into the thousands of degrees, causing them to glow with their own heat. In such extreme environments, the atmosphere might contain vaporized iron or titanium, with winds screaming at thousands of miles per hour. If clouds exist there, they aren't made of water, but of minerals and glass. JWST recently performed a detailed check on WASP 121b, where temperatures exceed 2000 degrees Celsius, hot enough to melt most metals. By isolating the planet's own radiation during eclipses, we've detected water vapor at high altitudes but a total lack of water clouds, suggesting the molecules are being thermally ripped apart. Then there is WASP 39b, a planet with the mass of Saturn but a puffy, bloated volume, JWST detected carbon dioxide, water, and sulfur-bearing molecules in its atmosphere, the first time we've seen such a clear chemical fingerprint on another world. This chemical cocktail challenges standard models. Some of these gases should only form far from a star, suggesting the planet migrated inward. Moving a giant planet across a solar system is no easy feat, yet the evidence points to a chaotic history of planetary movement. At the other end of the spectrum are super-Earths, rocky or icy worlds larger than Earth but smaller than Neptune. We have no equivalent in our solar system. Some may have thick atmospheres, others are barren husks like Mercury. LHS 475b, a world nearly the same size as Earth orbiting a red dwarf 41 light-years away, appears to be a rocky world but seems to lack a substantial atmosphere. Perhaps the star's radiation stripped it away, or it never had one to begin with. Then there is TRAPPIST-1e, a world that might sit near the freezing point of water, offering a potential laboratory for studying temperate atmospheres. Many worlds fall between categories. We see many Neptunes wrapped in thick hydrogen-helium envelopes, and lava worlds where the surface is so hot the rock liquefies into global magma oceans, with clouds made of evaporated stone. We find planets orbiting binary stars, planets with extreme eccentric orbits, and even rogue planets that wander the void without a star at all. While the JWST is just beginning to find these orphans, its infrared sensitivity makes it a lethal tool for spotting these lonely travelers. The traditional textbook model of planetary formation, where rocky planets grow in the warm inner disk and gas giants consolidate in the debris-rich outer disk, simply cannot account for hot Jupiters or the ubiquity of super-Earths. Instead, scientists now believe planets are nomads. They migrate after they form, dragged by gravity, pushed by gas, or slingshot by other planets. They are born in the cold outskirts and find a home in the searing interior over millions of years. The result is a cosmic gallery of wonders, acid rains, frozen peaks, alien chemistries, and skies we can barely imagine. There is no such thing as a normal planet, every world is an extreme case. In the coming years, JWST will observe hundreds of these worlds. Each is a spectroscopic story of gas, temperature, and clouds. If we are exceptionally lucky, we might even catch a whisper of life's signature, though that remains a distant goal. Perhaps the biggest surprise of all is that our own solar system might be the true outlier in a universe where anything is possible. That concludes our journey for today. May your dreams be as vast as the cosmos, and may you have a wonderful day ahead. We will see you in the next episode.